Hello, everyone. My name is Scott Vorthman. Welcome to the fifth day, second session of our week-long virtual Celebration of Mind event in honor of Martin Gardner. Today, I'm very privileged and honored to introduce my friend and fellow G4G board member, and indeed our program chair for the last several years for the Gathering for Gardner, Bob Hearn. Bob received his Ph.D. In computer science from MIT, studying under Erik Demaine, and Erik and Bob went on to, in fact, publish a book together entitled Games, Puzzles, and Computation. Bob has been a successful software entrepreneur. He's a highly accomplished ultramarathon runner, and we're very privileged to have him today. So with that, Bob, the floor is yours.
Thank you, Scott. Thanks for that nice introduction. So I'm going to talk about how, from my point of view, Martin Gardner is integrally connected to this vibrant field of computer science called reconfiguration. Now, we all know that Martin Gardner did not call himself a mathematician, but he has inspired a very large number of eminent mathematicians, computer scientists, and more. Here is a partial list of some amazing people who have been directly connected to him as part of his mathematical grapevine. A few of them we've been privileged to have speak here. Beyond this, I think it's fair to say that one would be hard-pressed to name a prominent mathematician or computer scientist who has not been influenced by Martin Gardner. But I don't think that anyone, at least I haven't heard it said, that Gardner is directly responsible for any particular field of mathematics or computer science, for helping launch such a field. And I'm going to kind of make that argument today. And so hopefully this will be a fun talk. There's a little bit of technical computational complexity stuff thrown in, but that's not the essential thing. The essential thing is the history, and I hope that comes through. So this talk is going to be a little bit unusual. It begins in the 60s and nominally ends today with the field of reconfiguration. But I'm not going to tell this the ordinary way. My talk structure is going to be a little bit more like the movie Pulp Fiction or Christopher Nolan's Memento, for those who are fans of those movies. Not that I expect there's going to be any violence unless somebody really disagrees with my narrative, but I'm going to tell the story in a nonlinear way. So I'm going to start in the past and work from the past and the present back to the middle, alternately working in from both sides. And the reason I want to do that is that's where the punchline is. The interesting stuff is the middle, the connection between Martin Gardner and reconfiguration. So hopefully you will humor me with this unorthodox presentation. So let's begin in the 60s with a couple of relevant Martin Gardner columns. This one on penny puzzles. Those of you thinking ahead can already see maybe the connection to reconfiguration. Penny puzzles, Martin didn't invent them. He, wrote a column about them, as he did many other things, made them people more well aware of them, but these puzzles go way back. The standard idea is you have some arrangement of pennies laid out on a table, and there's some target configuration that you want to reach that's different from the starting configuration. And you move one coin at a time in such a way that every move, you move a penny to where it touches at least two other pennies. So that's a puzzle. And he wrote this column discussing various such puzzles. Another relevant one from a couple of years earlier, this was 64, the hypnotic fascination of sliding block puzzles. This was a fabulous column. There on the front, we see Dad's Puzzle, which is a very well-known sliding block puzzle that dates back to the late 19th century under various names, like the Donkey Puzzle, Klotsky, or other names for it. You've probably played this puzzle. This takes 85 moves to solve. Once you get to here, you can slide that square out through the bottom in the version that I have. So Martin analyzed this puzzle in this paper, among other discussions of sliding block puzzles. But to me, the critical part of this paper, the critical paragraph, which is very prescient, is this one. These puzzles are very much in want of a theory. Short of trial and error, no one knows how to determine if a given state is obtainable from another given state. And if it is obtainable, no one knows how to find the minimum chain of moves for achieving the desired state. That's brilliant. And that's really sort of what the field of reconfiguration is all about today. So let's skip forward to the present. What do I mean by reconfiguration? That's just a word. All right, so here's what Wikipedia has to say. In theoretical computer science, reconfiguration problems are computational problems involving reachability or connectivity of state spaces. And in particular, we care about sets of configurations that are solutions to a combinatorial problem called states. So typically, we care about paths connecting solutions through a state space of solutions. And in particular, we care about computational complexity. Is this problem computationally hard, or is there an efficient algorithm? What's the diameter? How many moves does it take to get from here to there? This sounds sort of generic, and this, do we really want to call this a field? Because this is sort of a general consideration one might apply to a number of problems, but really there is a specific consideration here that has only become manifest in more recent years. I went to, so it's a vibrant field. There's hundreds of papers published in it. There's workshops, conferences. I went to a workshop in Barbados a couple of years ago. Here's the webpage for a workshop at the Banff International Research Station in 2017. Here's how they describe reconfiguration. It's the study of the transformation of solutions to a problem. The difficulty of solving the original problem may or may not indicate the difficulty of transforming one solution into another in such a way that the result of each step of the transformation is also a solution. So the key thing here is that you're starting with a problem that's already a problem. And let me get more specific. They give an example here in terms of power stations. I think the simplest place to start is with Boolean satisfiability. But before I do that, I have to talk a little bit about computational complexity, because that is essential to the story here. I'm not going to dive too deep, so don't get intimidated. But this is sort of the landscape that we're going to care about for computational complexity classes. So what does this mean? Theoretical computer scientists like to talk about, they analyze algorithms and problems. And in particular, we want to know whether some problem is sort of fundamentally hard, whether we can prove, or at least argue very convincingly, that there is not some efficient algorithm for a problem. And if there is, we want to find it. If there is an efficient algorithm, that means that the problem lies in the class P of problems that are solvable in polynomial time. For example, you can sort in n log n time. There's algorithms that are n squared, n cubed. If it's n to the 50th, that's still technically polynomial. It's not what most of us would call very efficient, but there's a sharp distinction between those polynomial problems and the ones that are out here that we call NP complete. For example, Boolean satisfiability lies there. The traveling salesman problem lies there. Many of you have heard of these as called NP complete or intractable, meaning that we know of no efficient algorithm for them. But there are larger complexity classes that are even harder in a sense. There's P space, there's X time, and we're going to care about primarily NP and P space here. Now, the central idea of what happens in complexity theory is that of reductions. If we want to prove something is hard, it really helps to know that something else is already hard. It's kind of a hammer. And the canonical NP-complete problem that we're going to use is called Boolean satisfiability, which you can also view as a kind of a puzzle. So here's how that works. You have a set of Boolean variables, X, Y, Z, and so forth, meaning these are variables that can take the values of true or false. And you have a Boolean formula. That's an expression in the Boolean variables using the logical connectives of and or, and not. And so if you pick an assignment for your set of variables, assign X to true, Y to false, Z to false, and so forth, that assignment is going to make that formula as a whole be either true or false, depending on the values of the variables. And so the satisfiability problem is this. If I give you a Boolean formula with a bunch of variables in it, does there exist any assignment whatsoever to those variables that makes the formula true? That turns out to be a very important thing in mathematics and computer science. And this was the first problem that was shown to be NP complete, and it spawned a huge industry of computational complexity results after that. It's also very frequently used, satisfiability is frequently used as the source of reductions for showing that other problems are hard. So how does a reduction work? It seems sort of backwards. We reduce from satisfiability to something else to show that it's hard. Here's an example, graph 3 coloring. Those of you who were with us this summer might have heard Colin Wright's talk, Colors Can Compute, where he delved in quite a lot of detail to this result that graph 3 coloring is NP complete, or colors can compute. It suggests there's something sort of computational about that. And there is in all these results. When you show that something is hard, there's an underlying element of this system supporting computation in some sort of abstract sense. We're not going to get too deeply into that, but I do need to illustrate what I mean by a reduction. So graph 3 coloring, the 4-color theorem is very famous. Most people know if you have a planar graph, it's always possible to 4-color it. So you assign every country or every node in a graph one of 4 colors, such that no 2 adjoining countries or vertices here have the same color. It's always possible with 4 colors. It's not always possible with 3 colors. Some graphs you can do it and some graphs you can't. And if we consider the problem of, I give you a graph and tell you and ask you, can you 3-color this? That is an NP complete problem. And that was shown by a reduction from satisfiability like this. So what is a reduction? What that means is that I have to have some easy way of translating a Boolean formula into a graph such that the resulting graph can be 3-colored if and only if the Boolean formula is satisfiable. So what does that give us? Well, imagine that there is some really efficient algorithm for graph 3 coloring, okay? Well, then that means because of this reduction, there's a really efficient algorithm for Boolean satisfiability, because I can always translate a problem in Boolean satisfiability into a problem in graph coloring and solve it there and get the answer. But we know that's not the case because Boolean satisfiability is NP complete. So if I can reduce satisfiability to something else, some other problem, X, then I know that X is also at least NP hard, could be harder. So that is an example. That's a brief tour of computational complexity. Now let's connect that to reconfiguration. And graph 3 coloring is a great way to make that more tangible. It's kind of a canonical case. We have here a graph 3 coloring of a particular graph. That's a solution to the graph 3 coloring problem for that graph. We can imagine there are other solutions. Let's say we have this solution A and another solution B. So the reconfiguration question is, can we get from A to B by changing the color of one vertex at a time, such that every step in between is still a valid 3 coloring? That's an example of a very natural reconfiguration question that people have studied. In particular, here's the paper that first studied this back in 2009. Suppose we're given a graph with 2 proper vertex K colorings, blah, blah, blah. Can we decide whether it's possible to transform alpha into beta by recoloring one at a time? This is p-space complete. Okay, that's sort of what reconfiguration is all about. I mentioned it's a very active, vibrant field. Let's just take a quick scan through some current publications. These are all papers from this year in reconfiguration. TS, reconfiguration of dominating sets in circle and circular arc graphs, reconfiguring independent sets on interval graphs, reconfiguration of connected graph partitions via recombination, distributed vertex cover reconfiguration. One of these I might have skipped over. It actually mentions as an application gerrymandering. Here is somebody who did his Ph.D. thesis this spring on reconfiguration problems in graphs. Okay, so reconfiguration is this active area of modern computer science. So let's jump back to the past now. Moving forward from the 60s, let's talk about the gathering for Gardner, because that's also going to be relevant to the narrative here. Most of you know Tom Rogers started the gathering for Gardner. The first gathering was in 1993. He had this idea of let's just get all of these Martin Gardner enthusiasts together in one place and see what happens, including Martin Gardner was there for the first one, and I believe the second one as well. This was so popular, it turned into a regular thing. There's now G4G every other year. G4G 14 is going to be next spring. It's supposed to be last spring. As we all know, that was problematic. So G4G is a thing beginning in the 90s, and let's continue to move forward from the past. This fascinating paper appeared in Theoretical Computer Science around about 2000, depending on which version you looked at. And that's about the time that I was beginning grad school at MIT. And Erik Demaine was a new faculty member there teaching an algorithms course. I was TAing for him. And Erik knew of my interest in puzzles. And so he threw this problem at me. He said, "Hey, Bob, here's this really cool paper showing rush hour is p-space complete. I wonder if we can look at the techniques that they use and apply them to ordinary sliding block puzzles, because that's been open for a very long time, as Martin Gardner first raised in 1964. So rush hour, I should have said, for those who are not familiar, is kind of a constrained sliding block puzzle. I see we have Bill Ritchie here in the audience of ThinkFun. This is a ThinkFun puzzle. It's a great puzzle. The goal here is to get the red car out of the grid. And there's cars and trucks that are sort of like sliding blocks, but they only slide forwards and backwards. They can't slide sideways. So this is an example of a constrained sliding block puzzle. And Flakenbaum came up with some really innovative new techniques to show that this was p-space hard. And Erik says, but can we apply those to ordinary sliding block puzzles? And so he got me hooked on that. And I worked on it and we thought about it for a while. And yes, we were able to show that sliding block puzzles are p-space complete. But the way that we did that was to find this sort of underlying problem formulation that is independent of rush hour or sliding blocks or anything, and has turned out to be very fruitful in game and puzzle complexity and also in reconfiguration. And that's called constraint logic. So let me tell you what constraint logic is. Our game board, if you like, is going to be a graph where all of the edges are either red or blue. The most fundamental problem here, which is not where we started, this came up later, but we can imagine this as the most fundamental problem. We want to find an orientation of all the edges of the graph. So each arrow points one way or the other that satisfies certain constraints. And what they are is not particularly important, but I'll just tell you because it's simple. The constraints are that at every vertex, we have to have either one blue edge pointed in or two red edges pointed in. And you can see by inspection here, this one has two red pointed in, this one has one blue, this one has one blue and one red. So the constraints are all satisfied in this graph. Here's a more complicated graph. This is actually the fully explicit form of how you cross edges, cross wires, essentially, in a constraint graph without using an explicit crossover. So everything here is planar, but effectively the signals propagate. So we might ask, okay, given this graph, is there a way to orient the edges? Here they're already oriented, but pretend they're not. Is there a way to orient all the edges such that the constraints are satisfied? That problem turns out to be NP complete. That didn't really occur to us until later because we cared from the start about the reconfiguration version of this problem. Can you go from this set of orientations to this other set of orientations, or even more simply, say we want to reverse this top edge here. We can't do that now because that would violate the constraints, but maybe there's some sequence of moves we could make that would let us reverse that. That's the problem that we cared about here in constraint logic. And that's the form of the problem that most people have used going forward as a source for reductions. And that's the problem that we use to show that sliding block puzzles are hard. Here's how that reduction works, just analogous to the reductions we talked about before. So again, what we want to do is come up with some simple way of translating an arbitrary constraint graph into a sliding block puzzle. And it turns out all we have to care about, this is part of what we showed, is planar graphs where all the vertices are one of two types, where they are red, red, blue, or blue, blue, blue. We call those and or vertices. And what that means is that to show a target problem like sliding blocks hard, all we have to do is show a reduction that shows how to reduce an and vertex and an or vertex to sliding block configurations, and a way to put them together to reproduce the semantics of the entire given constraint graph. And I'll just step through how this works. So this slide right here essentially is the proof after 40 years that sliding block puzzles are p-space complete. So this and on the left mimics the properties of that and vertex. So suppose we want to slide that top block in. First, we have to slide the left one out and the bottom one out, and then we can slide the top one in. And likewise, the or, we can slide either the left or the right one out, and then we can slide the top one in. If we're given a more general constraint graph, we would reduce it to some translate it to some sliding block puzzle like this. And the key thing, again, is that that translation has the property that this sliding block puzzle is going to be solvable if and only if the constraint logic graph is solvable. And that proves that sliding block puzzles are p-space hard. So, and so that answers Martin Gardner's question of 40 years ago. Why do we have no theory? Well, because there is no theory. There is no efficient way in general of answering the question, can we go from this configuration to that one? It's a hard problem, and this is why it's a hard problem. Okay. Let me go back to the future again and work backwards. We're gradually closing in on the middle here. This paper on the complexity of reconfiguration problems, the TCS 2010, I think the journal version was a year or two, or the conference version was a year or two earlier. To my knowledge, this is the first place that the modern terminology of reconfiguration is used. And this abstract here is very concise and clear and powerful. Reconfiguration problems arise when we wish to find a step-by-step transformation between two feasible solutions of a problem, such that all intermediate results are also feasible. We demonstrate that a host of reconfiguration problems derived from NP-complete problems are p-space complete. So that's a really important observation, because basically it gives theoretical computer scientists a whole new set of problems to chew on. If you're a theoretical computer scientist, you need problems. You need to prove theorems and publish papers. And what happened here was that Demaine and Papadimitriou and others pointed out that, hey, this is a really natural thing to consider. And we've got this massive pile of NP-complete problems that computer science has discovered over the last decades. And it's a very natural thing to consider the question, for each of them, can we, what does that solution state space look like? Can we go from one solution to another by changing one element at a time? That's an interesting thing to look at. And not only that, here's a set of tools for looking at it. And you might expect that in general, an NP-complete problem, when you do this, is going to be p-space complete. So hundreds of papers now, and people are getting more and more specific in the kinds of problems they're considering, because the low-hanging fruit all long since plucked. So this is when it was first made explicit, but the results occurred, this isn't the first time that reconfiguration in this modern sense was really considered in the literature. We can go back a little before this to this paper by Papadimitriou et al. This is the first place that reconfiguration of Boolean satisfiability was considered, a very fundamental natural thing. So we have that Boolean formula, and suppose we have a solution, an assignment of variables that makes it true, and we have another solution, and we want to know, can we get from this one solution to the other just by changing, for example, one variable at a time, so that the formula remains true. That's a very natural problem. It was first explicitly shown p-space complete here, and I believe 2000, depends which version of the paper, 2006 or so. But it doesn't begin there either. So let's go back to the past again and pick up this thread of the gathering for Gardner. And those of us who have been to the G4G know all about this thing called the gift exchange. My first Gardner, I was told, you want to show up with 150 copies of some new cool thing that you're going to show up and give this to the organizers. And when you go home, you're going to walk away with a bag full of 150 new cool things. What kinds of things? Think of the exchange as something you would be excited to share with Martin Gardner himself. We recommend something original or unique, or something other attendees would enjoy or value. So I started attending G4G in 2002, G4, G5. I like to use puzzles as exchange gifts and come up with new ideas for puzzles. It's always a challenge, and it makes it exciting for me. So 2004, we had G4, G6, and I was working on puzzles and games at the time at MIT. And I thought, I want to do a coin puzzle, a sliding coin puzzle, because that's something Martin Gardner wrote about. And I want to tie it, theme it very specifically Martin Gardner-y way. But I want to make it more interesting or more tricky or something, find some sort of hook that makes it new and different. And I racked my brains for a while, and I found a way to do that. So here's what the puzzle looks like. You've got this sort of graph laid out with circles with letters in it. You start with 4 coins on the bottom so that it says Martin. And the idea is to slide the coins on the graph edges So they're up here, and then it says Gardner. Now, as it stands, that's a trivial puzzle, but it turns out we can add a constraint that makes it much more interesting. And in particular, we're going to say you're never allowed to have two coins adjacent along an edge. Okay, so this is not a legal move. This is a legal move. It preserves that condition. So it turns out that makes this a much more challenging puzzle. So when I was coming up with this, I worked gradually towards this. I laid this out without the lines, with just the circles and the letters, and I thought, okay, what's something that might make this interesting? I said, okay, let's try this non-adjacency rule. Searched over all the space of reasonable ways to turn it into a graph, and this was the hardest. It takes 25 moves to do it. I played it by hand. It makes an interesting puzzle. Other people liked it and shared it and analyzed it. Cool, but I'm sitting there working on puzzle complexity at MIT. So I've just sort of come up with this new concept of a puzzle, and I have to ask myself, oh, well, is it piece-space complete? Can I analyze it? And the answer is yes. It's very simple to show that it's piece-space complete via a reduction from constraint logic, exactly like we did for sliding block puzzles. This is how you build an and an or vertex. You can see, suppose we want to move this coin or this token here inside this gadget, inside this and vertex. That's not a legal move. But if we slide this one out and slide this one out, then we can slide this one in. So that mimics the properties of a constraint logic and vertex. And the one on the right mimics the properties of an or, and I won't go into details. You give me a constraint graph, and I can translate that into a sliding coin puzzle that is solvable if and only if the constraint logic problem is solvable. Cool. Okay, so this new coin sliding puzzle is also piece-space complete. We can add that to the paper. But here's the thing. This is the kicker here in this talk. This is not an arbitrary constraint that I just came up with, not allowing two coins to be adjacent. This is a thing in mathematics and graph theory. Graph theorists care about this. This is called an independent set. A subset of the vertices of a graph, no two of which are adjacent, is called an independent set. And that's a very important mathematical concept that's already out there. In computer science, the independent set problem is one of the fundamental NP-complete problems. Namely, given a graph, is there some set of n of the vertices that you can choose so that no two are adjacent? So what does that mean? That means that we have discovered sort of a reconfiguration problem from starting from an NP-complete problem that says, let's look at the connected solution space of this NP-complete problem. And that is what reconfiguration is all about. Sometimes it takes a while in computer science or in any field for sort of the ideas to sort of come together so that you can look at them in a new way. So it wasn't really obvious at the time that there was this new field that was going to appear here. But so our paper came out in TCS in 2005. There was earlier journal versions, but this 2005 time gave us time to add this sliding coin puzzle, which we called sliding tokens. And we had this comment in the paper. This problem formulation is interesting for several reasons. It's a dynamic version of the independent set problem, which is NP-complete. It's natural to expect that many NP-complete problems become piece-space complete when turned into dynamic puzzles. So that's really the central the central observation, that occurred explicitly in that reconfiguration paper in 2010 that sort of manifestly launched the field of reconfiguration. But it's here earlier in this 2005 paper. And, maybe this idea, this observation exists earlier in the literature. I'm not really aware of it. I remember at the time thinking, this is really cool. It seems like a natural problem to go from this NP-complete thing and see what happens. And why has nobody looked at that before? And maybe people have looked at it before. I don't know. But this is the first instance in the literature that I'm aware of. And, it goes back to Martin Gardner. And so that's really the punchline. That's the whole point of this talk, is that there is a lot of serious mathematics and a lot of serious computer science that happens, but it all has to be motivated, or at least in many, many cases, it's motivated from a perspective that is all about fun and puzzles and problem solving and the recreational side of mathematics. That's the path that I have tried to explicate here from Martin Gardner to this entire area called reconfiguration. In more specific cases, that story occurs over and over again. And we all have Martin Gardner to thank for that. So I will stop there and take questions.
All right. Thank you, Bob. That is far and away the most fun I've ever had watching a talk about theoretical computer science. Thanks. Adam Atkinson asks, how often are G4G exchange items cited in academic papers?
Not that infrequently, I think. Sometimes people will use academic papers as their exchange items.
Yeah, no, that certainly happens.
Yeah.
From Barry, is the property that an NP problem turns into a P-space problem a general rule? I was wondering a similar thing. Are there exceptions that divide the space of NP?
That's a tough question. You know, this sort of goes back to a more general question in computational complexity of games and puzzles. It's long been observed that for any game or puzzle, you can sort of look at its general characteristics and know sort of what complexity class it should have. You know, like nickel-y pencil and paper puzzles, they ought to be NP complete. They can't be any harder because there's a bounded number of moves. And that's the same with like Boolean satisfiability. If you view it as a puzzle, you go and you choose the truth value of one variable at a time, and eventually you run out of variables, and then the formula is true or it's not. Those cannot be any harder than NP complete. And there's sort of this idea that because we're considering these cases that make interesting puzzles for humans, we should expect them to be NP complete. And it's the same for two-player bounded games should be P-space complete. One-player unbounded games like sliding block puzzle should be P-space complete. Reconfiguration problems between starting from NP complete problems should be P-space complete. I'm not aware of any result showing that there's any interesting or natural reconfiguration problem involving NP complete problems that is not P-space complete. That doesn't mean that that's not the case. You know, there's certainly cases that have nobody knows yet. Nobody's been able to show a result. You know, sometimes there are efficient algorithms, and there's always efficient cases. A lot of these papers that I cited are considering restricted cases. When you know, the computational complexity side of things, showing that something is hard, that's what's called a negative result in computer science. There's also the positive results. If you're analyzing algorithms, a negative result says, oh, we can't do any better than this. Positive result is, oh, here's this case where we can do it in n squared or n log n. And so there's lots of cases in these papers on reconfiguration where they say for this particular class of graphs, this reconfiguration can be done with this efficient algorithm. So there is that. Mario is NP complete, yes.
Do you know if there are any systems that use constraint graphs for solving reconfiguration problems or say planning problems?
For solving, I wouldn't think so, because I mean, these are hard problems. Constraint graphs and constraint logic in general is a very commonly used tool in the field of reconfiguration and more generally in game and puzzle complexity, because there's only two gadgets you have to implement and you can do it with planar graphs. And so it really just turns out to be what you want for games and puzzles or anything planar, really. But in terms of using it to solve things, no, not so much, because it's a hard problem.
It looks like our questions maybe have tapered off. Thank you, Bob. Again, a delightful talk. I've never enjoyed understanding a reduction more than that.
Cool.